Okay, next we will calculate the kinetic energy of the wave. So kinetic energy of dx part, kinetic energy of the small length element dx part is, I call it kinetic energy Ke, which is equal to dk, sorry, I call it dk. Kinetic energy dk of this dx part is 1/2. Now we have mass is now dm, like the length element dx has a mass we consider to be dm. Here we consider this length element to be dx and its mass is dm. So its kinetic energy will be 1/2 dm into vp square, where vp is the velocity of the particle. Velocity of the particle, or we can say that the length element dx. Velocity of the particle or the length element dx. And we can calculate the velocity by using this formula. Vp is equal to dy by dt. Now d by dt and y has a value, that this is the wave equation, which is a into sine kx minus omega t. Now a is constant, so I'll keep it outside of this derivative. So we have d by dt of sine kx minus omega t. If we take the derivative with respect to t of this function, we get what we call it minus omega, and then we have a into cos kx minus omega t. This is vp, and here we have this vp square, so vp square will be omega square a square cos square kx minus omega t. So using this value in equation, I call it, this is equation 6, so I call it equation 7. In equation 7 we have, so dk, which is equal to 1/2 dm, and then we have omega square a square cos square kx minus omega t. Now if we further simplify it, by further simplification I means is we have to put the value of dm from equation 1. This is equation 1, dm is equal to mu time dx. So if we put it here, then dk will be equal to 1/2. Now this dm is mu times dx, and then we have omega square a square cos square kx minus omega t. We can write it as dk, I'll bring this dx to this side, we have dx, which is equal to, here we have mu and here we have omega square a square divided by 2 into cos square kx minus omega t. This is the kinetic energy per unit length. This equation this equation shows the kinetic energy per unit length, and I call this equation is equation number 8. Now we have two equations. One is equation number 6, which is for the potential energy. One is equation number 8, which is for the kinetic energy. So we have the equation for the potential energy is du over dx, which is equal to mu omega square a square over 2 into cos square kx minus omega t. And similarly for kinetic energy, dk over dx, kinetic energy per unit length, and this is potential energy per unit length, which is equal to mu omega square a square over 2 into cos square kx minus omega t. Now these two equations shows that, kinetic energy and potential energy have the same value, because the right hand side of both these equations are same. Mu square omega square a square over 2 cos square kx minus omega 2. So whatever the value of potential energy, that will be the value of kinetic energy also, because both these equation the right hand side of both these equations are same. So if we got, let's suppose this side to be, let's suppose 10 joule, then this side will also be 10 joule, because all the parameters are the same. Like if kinetic energy is maximum, if this equation give us a maximum value, then the potential energy will also be maximum. So this equation will also be give us a maximum value, because this side and this side, they are both equal. So we can say that du over dx is equal to dk over dx from these two equations. So the kinetic energy per unit length is equal to potential energy per unit length. Now the total energy per unit length, we can say that the total energy is dE, which is equal to dk plus du. Change in total energy will be equal to a change in kinetic energy plus change in potential energy. Total energy per unit length dx, I will divide throughout this equation by dx. So we have dk by dx plus du by dx. I can write it as like this: total energy, which is E, which is equal to the sum of kinetic energy and potential energy. So take the derivative with respect to x. dE over dx will be equal to dk over dx plus du over dx. This is the total energy per unit length. So total energy per unit length is equal to kinetic energy per unit length plus potential energy per unit length. So kinetic energy per unit length is given by this equation, potential energy per unit length is given by this equation. So if I put it here, we get mu omega square a square into cos square kx minus omega t. So there is a difference. Here we have 2, here we have 2 in the denominator. Here there is no such factor in the denominator of this total energy per unit length. So it means that if kinetic energy is maximum and potential energy will be maximum, because both have the same relation. So it means that total energy will also be maximum there. If kinetic energy is minimum, then potential energy will be minimum at that point, then the total energy will also be minimum, because this part is exactly equal to this one, or exactly equal to this one, which is not the same in the case of simple harmonic motion. In simple harmonic motion, if kinetic energy is maximum at some point, then the potential energy will also be maximum at that point, while the potential energy will be minimum at that point, while the kinetic energy will be maximum at the total energy will be maximum at that point. I can repeat it again. If let's suppose we consider a given point where the kinetic energy is maximum in simple harmonic motion, then the potential energy will be minimum there, while the total energy will be maximum there. So here the case is different. If kinetic energy is maximum, potential energy will be maximum there, and total energy will also be maximum there. So this is the only difference. Now I will explain where the kinetic energy is maximum and where the kinetic energy is minimum. So for that, I will consider the simple wave train, the simple wave in a string. So we have to remember that we have dk over dx, which is equal to mu omega square a square over 2 cos square kx minus omega t. This is for the kinetic energy. Similarly, for potential energy, du over dx is equal to mu omega square a square over 2 into cos square kx minus omega t. This is for the potential energy, and the total energy per unit length is mu omega square a square into cos square kx minus omega t. Now I will consider the simplest case, which is the wave in a string. Suppose this is the string, so the wave will be like this. This is the support where we connect the string, and here we are applying the force up and down to produce this pulse in this string. Now I consider 2 points now. One is point, I call this is point A, and I call this is point B. Now first we consider the point B. Now at point B is the maximum amplitude, because the amplitude is maximum here. This is the maximum amplitude, and we know that when a particle reaches to its maximum amplitude or maximum position, then the velocity will be 0 there. The particle goes there, stop there, and then again move down. So once it stop, it means that this particle is at the maximum position. So here the velocity is 0. If velocity is 0, then kinetic energy will also be the 0 here. We can say it's minimum. By 0 I means minimum. Now if we look at point B, suppose I will consider 2 neighboring points close to this point B. One is this point and one is this point. So if we plot a perpendicular on this one, so here we have dx, so here the length also dx. So there is no change in the length. In other words, I can say that at point B the change in displacement dx is 0, because both this length are the same. While in the previous case we have different length. This length was not exactly the same as this one. If the length is same, there is no change in displacement, so it means that the work done is 0 there. If work done is 0, then the potential energy corresponding to that work done is also 0. So potential energy will also be 0 or minimum. So it means that the total energy E will also be minimum there, because the total energy will be equal to the sum of kinetic energy and potential energy. Now if we look at point A, this is point A, then this is the mean position of the particle, because this is the string which is at rest. Then this is point. If it's moved, then we have this, we have produced. So this particle is at mean position, and we know that when a particle reaches to its mean position, its velocity is maximum there. So it means that if velocity is maximum, then kinetic energy will be maximum here. Now if I consider 2 neighboring points close to this point A, one is this point and one is this point. If I plot a perpendicular here, then this is dx, and this is dl. dl is now this one. So dl is this one, from here to here. This is dl. So dl is greater than dx. So we have a displacement here. Displacement is dl minus dx. So there is a displacement, so this displacement is due to work done by the tension force. So if there is work done, there will be a potential energy. The displacement is maximum here. So it means that the potential energy is also maximum, while the total energy E will be maximum also. So this is the reason we say that this wave motion is different from the simple harmonic motion, because if we wave motion at a given point, let's suppose point B, if the kinetic energy is minimum, then potential energy is also minimum here. While in the case of simple harmonic motion, if kinetic energy is minimum, potential energy will be maximum there. Now the total energy remain conserved in simple harmonic motion. Suppose if I consider this point or this point, at both this point total energy will be the same, but here the total energy is minimum at this point B, while at point A the total energy is maximum. So the total energy also does not remain constant. So this is the only difference between wave motion and simple harmonic motion. Now I will discuss how energy is transferred from one point to another point during wave motion. So for that I will consider again the same case. So we have this is, let's suppose, the wave train produced in a string. I consider again the minimum and maximum point. This is point A, this is point B. Now at point A, at point B, the total energy is minimum, while at point A the total energy is maximum. This is not point. I consider two particles, I consider two particles. One particle is particle A and the other one is I call it particle B. Now particle B is at the maximum displacement. So at maximum displacement we have the kinetic energy is minimum, potential energy is minimum. So total energy is also minimum. So the total energy of this particle B is minimum here. I call this is point 1 and this is position 1 and this is position 2. While this is particle B. Particle B is at mean position, and at mean position we already discussed here. Kinetic energy is maximum, potential energy is maximum, total energy is also maximum. So total energy is also maximum. Now this is a wave in a string. This is position 1 and position 2. Now how we can define a time period? The time taken by the time taken to complete one complete vibration or one complete oscillations. So the total time is T. Now if this particle now start moving from here to there, it takes time T over 4. Then again from here to here, it takes again time T over 4. T over 4 plus T over 4. Then again if it's move from here to here, it takes time T over 4. And then from here to again here, it takes time T over 4. So the total time is again T. Now after time T over 4, because this particle is oscillating back and forth, up and down during the wave motion. So after time T over 4, after time T over 4, what will be the situation? Our original wave is like this. I just consider only these 2 pulses, 3 pulses, yes. After time T over 4, what will be the situation? It looks like this. This particle B reached to its maximum position, maximum amplitude. So we have this one. So here we have this situation. Here we have this one. So it's like this. So I will use a bold thick line for the next time. This is when time t is equal to 0, and this is when time t is equal to 0, yes, when time t is equal to t over 4. So after time t over 4, this particle move from this mean position to this maximum displacement, and this particle B move from maximum position to this minimum displacement here. So it means that now particle BA is here and particle B is here now. Now here the energy, total energy is minimum. I can say 0. Here the total energy is maximum. So initially the maximum energy was here. Now the maximum energy transfer from this point 1 to point 2 here. So by this way energy transfer from one point to another point. Initially this particle this particle is a maximum energy, this one is a minimum energy. Now this particle goes to a energy with minimum energy, and this particle goes to a position 2.2 where its energy is maximum. So energy transfer from minimum to maximum. I can say the energy change from 0 to, let's say maximum energy is 10 joule. Now this position, this point, this particle has energy now 0. Before it was 10 joule, and the particle B has an energy of 0. Now particle A energy becomes 0 and particle B energy become 10 joule. So by this way we can energy transfer from one point to another point in a wave motion. So next I will discuss power in a wave, and then we will discuss intensity. Thank you.